Swayam Prabha. Digital India. Educated India.
Good morning, everybody. My name is Ganesh Tyagarajan, and I'm originally, my BTech is from IIT Madras, 1980 to 85, last 5-year batch. And the 4-year batch started, first one was 81, so there were 2 batches graduating at the same time then. I also did my master's here, MTech, MS actually, they had MTech and MS. I did MTech here, MS here with Professor Kalyan Raman. And so he was my guide, and then first of all, I welcome everybody to the GAN course on the response and design of structures for blast loading. And it's a fairly interesting subject. I got into the subject about 17 years ago and have been working on it, on different aspects of it. I'd like to first of all thank Professor Aragappan, and we put forward this proposal about 1.5 years ago. And I also like to thank Gyan for this opportunity to come back, especially for me to come to my alma mater and be able to have this opportunity to share whatever I know about it, a little bit about in this subject. And so briefly, my education is, I worked in Government of India. I was an engineer through the, IES exam, it used to be called then. I think I was the only IITian who wrote IES. And so I worked in the Government of India for 3 years in Delhi in the civil construction wing of All India Radio. Then I went to do my PhD at Louisiana State University in 1991. I finished 96 in computational mechanics. I did work for an Air Force project on composites, cyclic behavior of composites under behavior of composites actually under cyclic loading, molds, metal matrix composites at that time, and for aircraft structures. Then I spent a year in University of Illinois, Chicago, Urbana-Champaign, not Chicago, Urbana-Champaign. As a postdoc, worked on an RP project on armors, protective behavior of armors for tanks. And then I taught at Louisiana State University for about 6 years. And then I've been, as you can see, been at University of Missouri, Kansas City since 2002. And so 23 and a half years, 20 going on right now. And so some of the things you can see have several projects. My research areas are focused on 2 different, one is on dynamic behavior. I've worked in seismic at one point. I've worked in a lot of experimental work in FRPs and structures. I've also worked in bridge areas, design of bridges, load rating, and I do work for MoDOT time to time when we get projects from them. But focus over time has been on blast behavior of structures, especially concrete structures. Now I'm doing slightly different things, but blast behavior itself. Then I also work on bone since computational mechanics, I was just telling Professor Aragappan that computational mechanics is so vast, you can adapt it to anything. So I started working about 17 years ago again in the behavior of human behavior, structures. Bone is a structure, and so I've got several NIH projects I've worked on and have one right now where we study the effect of loading on the development of bone. In terms of my experience in professional side, I recently finished 2 terms as the chair of the American Concrete Institute. 370 is the committee, like ACI 318 is the main code, like that 370 is the Committee on Blast and Impact Effects. So we have a primary document there. So concrete structures, if anybody wants to You can look at that document. It has some very nice details on that. And then I also served as a chair of finite element methods in concrete structures, 447. And then I've worked as volunteer as associate editor in ACI's structural journal, ASCE Structural, Journal of Structural Engineering, and also Journal of Materials and Civil Engineering. And there's some of my recognitions. That's not as important. And right now I've got a couple of projects. One is working for the Army and the other is working for NIH. Those are fairly large projects that are active right now. So that's a little bit about me. We designed it in a way to start with a lot of introduction to different things, and then after in the second session we'll go into risk analysis and then go into tutorials. So that's the plan for today. So what are different learning objectives of this particular course? So basically, to describe the nature of blast loading on buildings. And how the effects of shock wave. We'll talk a little bit about shock waves and other types of waves that are caused by detonating products. And I'm not an expert in explosives at all. I just know enough to apply it to a design perspective, because there's a lot of shock physics that is involved, which is highly specialized. I do work on numerical simulation, but again, I use the whole thing as a black box. We'll talk about that later on. So if you're looking for shock physics and how explosives go through, you might have to take another course on that. We learn to recognize not just concrete structural elements, but we'll also look at steel. I will also look at some precast construction. If we also have some examples on masonry, so different types of structures. And I did work a lot back in my engineering days when I was as a field engineer in using IS 456 and IS 800, but unfortunately I've been last 30 years using ACIs and AISC documents. So some of my design presentations, I'll explain those fundamentals, so I'm sure you'll be able to relate to that as well. And one of the reasons we are doing some of these things is the UFC that I'll talk about shortly. A lot of units are also based on the FPS or the US customary units, as they're called, foot-pounds and seconds, rather than the MKS or the SI systems, because the documents that we will use are based on that unit system. But it's easy to convert, and we'll see if we can provide some conversions as we go along. So you'll recognize the elements, how they perceive the loads, how to convert a complex wave phenomenon such as a shock wave into a load that is transferable for design purposes and for analysis and design. Then we also look at the different analysis and design options available to the engineer. In terms of analysis, we will look at a basic single degree of freedom analysis. You can do a lot of elemental designs just using single degree of freedom systems. And of course, if you have done structural dynamics, you know there are limitations to it. But when we convert any complex phenomenon into something that's practical, we have to have tools that an engineer can use without a whole lot of background. So SDOF works in many ways. Complex analysis, as we will see, it has its own limitations, accuracies, modeling efforts, and so on and so forth. But we'll look into a little bit. I think over time you do have next week there are some tutorials on using some finite element analysis so that you get a flavor of that as well. We'll talk about some design criteria. As you see, there are several serviceability criteria in steel, concrete, at least in the US codes. You have service loads, and you also have various criteria for deflection limits or rotational limit, so on and so forth. But here, the design criteria is based on sort of, they don't quite call it performance based, but it is in a way performance based. The levels of protection, or the LOP, as the LOP as we will refer to it going along. What are the different conditions that are associated with different levels of protection? And then this course is all based on open source material. So you should be able to download, we're providing some of them here, but we'll see what are all the different available resources and references. And I keep, even yesterday, I was reading an article, and there's so many new things you keep learning, reading articles from different perspectives. What we will do is, okay, there we go. So we will also, the reason I use this is a very simple software. I use this extensively in all my classes because you can easily convert it into a PDF and then upload it, and you can download it later on. So some examples, of course, we have a few examples in India itself. This is the Twin Towers that you've seen, 9/11 that you have seen, and this had actually fatalities were almost 2,000, 3,000 fatalities. Did I close it? I think. Okay. So this was in this had both blast and impact. Now they are two different phenomena. Physics-wise, they are two different phenomena altogether. We can consider, we'll see if we can give an introduction to impact, but that really will be just barely touching on the surfaces. This course will focus on the blast effects on structures, because the physics, the designs, equations, everything is very different, as some of you who are working in this area know about it. Usually, unfortunately, in structural engineering, or disaster is what motivates further research. If you see back in the 1970s, there were some extremely heavy earthquakes in the US, especially in the San Francisco, in the West Coast. And till then, the research in seismic design was fairly minimal. But since that time, over the next 30, 40 years, they've poured in over $1 billion just in research alone. And unfortunately, all these disasters are what forces us to do further research. And that's what happened here as well. So this was in Khobar Towers. This is a residential complex. And as you see, this structure was clearly not designed for blast effects. As you can see, all these are basically what we will call as curtain walls. So most likely there is a masonry wall here, and there is another masonry wall. Oh, I think if I keep my finger, yeah. So all these were separate walls. So clearly you can see the walls blown in. And so observations like this prompts us to provide for ways to not design in traditional manners. Then the other effect, now this is the Oklahoma City bombing. All of these, as you see, are fairly recent, 1990s. And this is actually very close to where I live. I live in a place called Kansas City, which is right in the middle, like Nagpur in India. It's Kansas City in US. And this is about 2-3 hours from where I live, maybe 5 hours from where I live. So this was a federal building, has a courthouse. So in the US, all the federal buildings, government, that is the main government building, central government buildings, are all governed by a certain set of criteria. They are not Department of Defense criteria. They are under what is known as the General Services Administration. So GSA has their own guidelines on design. So all these were designed originally as per GSA guidelines. The problem with this building is this was in a parking garage, underground parking garage. There was a truck bomb that was placed near a very critical column. So when that blew up, that definitely blew that column away, but still a concrete building is designed for a lot of load distribution, redistribution. But what happened here is it was not designed for progressive collapse. So the main failure of this in terms of fatalities and all the things that you see, this was mainly progressive collapse. And so the principles of progressive collapse, if it had been applied to this building, perhaps it may not have had the effect, the impact that it has had. So that prompts changes to the guidelines in terms of progressive collapse and how to introduce those principles. And there is a UFC for that also we'll talk about. The other incidents maybe I'll talk about is in terms of the Mumbai, I think the Taj. There you had almost 250 plus fatalities and also about 700 plus injuries. And then the other one is also the siege. I think I do not know the time, you might know it better. This also had in terms of 160 plus, and in terms here it is 300, let's say, plus injuries. So the effects of it can be fairly devastating. But what we see all this is an unusual event. So the thing to keep in mind in terms of design, just like you have in wind, you have return periods, and in earthquakes, same thing, you have return periods. Of course, now there are other ways to quantify earthquakes. So same thing here, there is no return period. You never know what is going to happen. It's so many different factors, and that's what we will look at later on in the second session today. So what are all the different considerations when you are getting into a blast design? First thing to keep in mind is this is going to be an unusual event. So how to consider for an unusual event? The threat loading, when you look at dead loads, live loads, earthquakes, seismic, wind, whatever, they're all well defined. In the US, we use ASCE 7, now it is 22. So anything as far as, it's a standard. ASCE 7, as you may or may not know, I think India also may have a equivalent to ASCE 7. So if you see ASCE, anything for loading purposes, you go to ASCE 7. ASCE is the American Society of Civil Engineers. So they have committees, and the committee 7 works. It used to be, when I started teaching, it used to be a very small document, but now it is now such a thick document because they incorporated all the seismic practices into there. That's what I keep thinking. The Eiffel Tower was designed 100 plus years back, and the code was probably, may not even be a code at that time. It still stands, and it's one of the most popular civil engineering monuments. But now we have sort of boxed ourselves into so many constraints and very standardized buildings, but it is needed as the time goes. So here, the threat, the loading is in terms of definition of what is known as a design basis threat, or DBT. So that is specified in terms of the explosive charge weight. So the charge weight, I work mostly in pounds, or you can use in kgs. And this is different types of explosives. We never know who's going to use what's available. And then there is also a standoff distance. So what we mean by this is, suppose this is your structure, and that's your so let me denote explosive in this way, and we'll talk about where the explosives are faced are placed. So this is the um, so this is I think it's my wrist that it is recognizing. So anyway, you can see this is R going up to there, and this is the weight W. Then for economic design, just like some of you said you're working in seismic design of structures. So in seismic design, in normal designs, even though we have in US, of course, strength design, and there is also, of course, stress design is out, but it's an equivalent of it is there called ASD, allowable strength design in steel structures. But in all those cases, those are all factored loads. And here, when you are designing a normal, somebody said tall structures, you're still designing at peak capacity. Every room filled with live load at the same time, the behavior is still fill in the blanks. It is elastic, right? It is still elastic. So think about that. You are designing for plastic considerations, but of course under factored loads. So in seismic, and depending on again the expected performance, in seismic now you have performance based designs and more. So depending on that, you do have to go to plastic design, and we'll talk a little bit about designing for plastic behavior. There is a session on that as well, elastoplastic behavior. So more plastic behavior, or in this is elastoplastic behavior. Then we talk of again these are a lot of, I mean, when I'm picking up a new subject especially, I throw away all the articles and prepositions and just focus on some keywords, right? And you can really pick up the subject much faster. So things I'm highlighting are basically terms that we will be using quite frequently. So this is, for example, the next thing is we talk of the level of damage. Now, the damage is specified basically in terms of, it's very straightforward. When we look at an element design, and let's say we consider simply supported structure, and it could be other conditions as well. So we are assuming your deflection is in this manner. So in certain structures, the deflection limits are, so you have deflection limits out there. Steel, for example, you can have, it's easy to define deflection limits because steel is not going to collapse. But then when you start looking at masonry, or you can start looking at concrete itself, is really difficult. And some of you are working, I heard somebody say working in concrete, and I've worked in experimental behavior of slabs. It's really hard to define what the deflection is. You might have your laser measuring devices, you might have other devices that are measuring your deflections, but at what point it stopped being deflection, damage starts, and then the deflection is due to loss of the stiffness in the structure itself. So quantification issues can be a challenge in those types of structures. Masonry, concrete, precast to an extent, pre-stressed probably you can do a lot of deflections. In the US, actually, you'll have specifications for all these in a very different way. So in those types of structures, you take the same deflection, and instead of measuring the deflection, this is still the delta, but now you measure the support rotation. So basic, very simple relationship, tan theta is delta over L by 2, or theta is approximately, and so specified in degrees. So that's your, so you'll expect to see specifications in terms of member deflection and support rotations. Another thing we consider here especially is the material strength. So basically your concrete strength, if it is 4 ksi, or what 1 ksi is about 7 megapascals. So approximately, let's say, if you are designing it, you'll design it for 4 ksi in the US, and here perhaps in 30 megapascals. So you may have limits. Material strength is mostly higher, so you may have what are known as strength increase factors. We'll talk about that later on. Or these are also called as SIFs. And same thing with steel also, different materials will have different strength increase factors. And finally, the limit state with the resistance factors, we use the load and resistance factor design, LRFT, and there they have different factors. For example, in bending, in depends on the type of material, steel or concrete. So steel, for example, in bending could be 0.9, or in shear this is 0.75. These are strength reduction factors, but in blast we assume that it goes all the way to 0.1. So in terms of the design philosophy, the starting point is always the building layout. So you should, if you're working in the US, buildings that are designed for blast, nowadays bridges are being considered, although codes have not incorporated. People are working on it. There are guidelines, there are books, or there are articles on that. But in buildings, all DoD structures, all embassies, there are State Department structures, and all federal buildings, they're all designed for blast resistance. And the starting point is always a building layout. For example, if this is your available land, in this case, things to keep in mind is, suppose this is your building layout here, and let's say you have a shape of a building like this, and your road, this is your access roadway. Things to consider in design are what is these distances, R1, R2, so on and so forth. And then other things to consider, these are just a few examples, and this would be R3, these are all standoff distances. So the New York, if you see, there was a New York city bombing, same thing, but that was adjacent to a road. So whereas other types of structures, if you can design and if you can afford it, the standoff distance, this is, as you will see later on, the most important element in preventing any failure for the structure. The more standoff the distance, the better it is. So if you can afford it, and if you have to keep certain other critical structures, for example, you have your computer room or anything that is critical, you have your HVAC facilities, as long as they are away from access, you orient them, and this is something you have to work with the architecture. Quite often architects are the first people to start this process, but in this case, as a blast engineer, you have to get involved at that stage itself and work with the architects. So the building layout is one of the most important aspects of it. Decide what needs protection. There are two things. Quite often of course, in seismic there are categories, building categories, based on whether it's a hospital, fire station, or a normal structure. But here the contents go beyond that. contents, as you will see, there's a whole array of contents you consider, starting from people. So people safety, any other network, anything that is critical equipment that you think for a structure, all those things, if you are, it's a law office and you have to store records, all those kinds of things become important in the design of the structure. And of course, building itself needs protection. As you will see that often the design of buildings is the last layer of protection. If you can avoid it, that's the best way to do it. I know it doesn't help us to bring our expertise into the picture, but safety is the most important thing, so that's where we start. So how the building should be arranged to give the desired protection. Another thing that happens here is, for example, this is a re-entrant corner. So if you have so let's say if you have in this place, this should be away, so this is away from the source of the blast. You're able to see what I write, right? The size wise? It's fine. Okay. So let me know if you have any questions. So meanwhile. So any questions again so far? Successful with 7 pages. A re-entrant corner is where, for example, suppose you have a building like this, right? And you have, let's say, this is the flow. And now this corner, you can have vortices, right? So that is a re-entrant corner. So because here if you see the flow, this goes in fluid mechanics. Flow goes around here, but here the flow goes in, it can get reflected, and here there is a lot of turmoil that goes on, vortex type. And the reason you avoid those kinds of is re-entrant corners. That's something, if you can completely avoid, that will be the best scenario, because that way the uncertainty in the prediction goes down more than anything else. So we looked at how the building should be designed. So the next thing is, what are the building design requirements? As we talked about it, the primary things, considerations that go in are the so there is actually another I think we missed it. So let me add that. So some of the guidelines here are, one is you first assess the requirements of the client. Then you're looking at, once you have that, the design feature. And I must mention here that design, quite often the client knows what they want, but this is, as a blast engineer, you have to educate people on what they can expect. It's not a product they get and you expect and they get what they expect. Because of so many uncertainties involved, at least we advise every engineer who works in this area to clearly tell the client that what they get out of it need not be, but these are what we know are the best practices. The word we use is best practices in the field. Just like doctors, they use the best practices available. Outcome is, it just depends on person to person. In a similar way, we take the same approach. Then The next thing to consider is the building form and facade. And then we go into the structural design itself, analysis and design. And then finally, we look at some of the internal design aspects. For example, glazing, it's still in doors. Doors that are opening out is better than doors that are opening in. Minor considerations like this should be taken into account when you're designing internally. So the building design requirements, main things are to deflect the attack by layout, security, or it also could be by external devices to deflect, such as bollards. These are very commonly used, or you have your walls, protective walls outside. So these are some things to deflect an attack. And then if you have, the next thing to look at carefully is what are all the different, why is that particular building being targeted? And people are not choosing a building out of random choice. There is a reason they go the Pentagon attacks, for example, or the Twin Towers. So it creates a lot of, the mission is accomplished by choosing targets that are of high value. So disguising the valuable parts of a potential target, and then how to disperse it, a potential target, so that any attack does not cause a significant damage. And then, of course, the best ways are, you'll see all the security, TSA, especially things like that. This is to stop the attack. And if it does, this is where we actually, so the design, as I had mentioned earlier on as well, this is literally the last aspect of any design of a building for blast. So I think I was a little ahead, so here some of it is repeated. So what are we'll look at each one of them, the requirements of a client. So the first requirement, the 4 different things we'll look at, let's consider a typical commercial multi-story new building. And then first of all, it is expensive to protect against blast. So as an engineer, you have to consider why it is needed. And if they move forward with it, that is to be an education coming from you based on rationals. You come with a reasonable calculations. Whatever we do this afternoon, we'll take up and say, this is why, this is what it takes to protect that particular building. Because the clients, architects and engineers, they have a number of choices. So the role of a designer is to advise the client based on basic principles. And some of the basic principles is what we cover in this over the next 10 days. Then advice guidelines, remember that do not ensure that the building is fully protected. You have to clearly state that these are the best practices, and that's from the requirements of client. And how do you convey these requirements? If it is a building on an offshore, we have, for example, ASCE 7, or it's a building on a coast. You know potential for cyclones, hurricanes, what kind of wind speeds there are. So we really don't need to tell a client, as an engineer, I go to ASCE 7, I look up the wind speeds, I know from there I calculate my pressures, and I can go about designing the building. But here you have to talk of what are the different LOPs and where is the client comfortable in this case. We'll talk of different LOPs, how they come into the picture later on in this course. Other things, blast mitigation, we'll cover a little bit of it later on. Hardening the structure is basically adding components in addition to the primary structure, such as polyurea coatings or other such things. You want to harden the structure. Blast mitigation is additional things that you add structurally in order to reduce the effect of the shock on a structure. So things that get most affected, which as a structural engineer we don't ever get into, is glazing design. I've worked with glazing experts and they do their own analysis, different types of glasses they come up with. So structural engineers rarely get involved in glazing design. But here it's good to have an idea of some, because that is the one that is most affected in any blast environment. What are the claddings? So claddings are nothing but the walls that you've seen that blew out from that Kobar towers. So similar picture like that. So that is what claddings, so these are basically non-structural walls. Other building services, HVACs, lifts, elevators, those kinds of things, and then finally the frame. So the level of protection leads to the consideration of the size of the explosive device. And we'll look at a few different types of explosive device. So you help the client define the size of the device. So basically this is the weight in kilograms, and define the limits to the extent of damage. This is again based on the level of protection. The other things you can advise them on are, this is based on your deflection limits or support rotation limits. So advise them, if it does go, the structure can say go 8 degrees of rotation, what it actually means to a client. How does it convert into what they have to do once that event has occurred? Then a little bit on design features, and again this is very subjective. We'll just talk about it. So standard building design features can be at odds with blast protection and resistance. So this is something we all should be aware of when we get into architect engineer fights are very well known, right? You never see eye to eye. This can be even more challenging. So for example, floor to floor curtain walls in multiple stories designed for regular loads can be a hazard. So you're changing the entire philosophy of that structure itself, right? So many buildings you see out here, what do you see? Columns and beams, the structure goes, and then they come in and put some masonry wall and you're done. But that's completely contrary to blast protection. That is a no-no in that case. So form of facade failure, loss of life, internal finish, all these are different things that we have to consider. Then looking further, building form and facade, the exterior should be simple and essentially convex in form. Now, why is this the case? We'll talk about a little later on the type of pressures that occur due to a shock loading. There's, just to give context to it, there is what is known as an overpressure or an incident pressure. There is a reflected pressure, and convex structures, and there is also diffraction. Convex structures tend to smoothen the airflow around it, sort of the wave flow around it. So that reduces the resistance effects. So that's why convex forms are preferable, circular convex forms. They allow for the loads to dissipate more effectively than any rectilinear form. Undesirable, as they enhance the effects are re-entrant corners, and somebody asked about it, cantilevered upward floors and decks. It's very, very common, right, to have, um, even in the lobby area, it's very common to have 8, 10 feet entrance area where cars come in, and those are some things that can be, especially in a public building, it can be very, very dangerous, or how to mitigate or how to avoid that are considerations you talk with the architect. So re-entrant corners we have talked about. Recesses. So a re-entrant corner is, if this is the building, that's your re-entrant corner. And recesses, if you see, this is nothing but a building. So this would be a recess. And here also you can see that there is a lot of complex. So the wave or the pressure wave on the structure can be fairly complex in these types of. Then internal courtyards and arcades, they can be beneficial, undesirable in this case. Again, this is an internal, but that can be a place where people use that as a source of an explosive. So if you're getting into it, if you're not able to get a truck bomb or a car bomb, multiple people can get in with suitcase bombs and others, and that really becomes a danger spot. So these are some things. You may not succeed with a lot of these ideas with the architect, but these are some things that you can, as they say, educate the architect about and let them make the decisions. If you look at features that facilitate our minimum glazing considerations, although there is a lot of research that has been done on different types of glasses, using single layer, double layer glasses that don't shatter, right? So using PVB layers in between. So those considerations can still be adopted, and that's why we will touch briefly on how thick a glazing should be. It's just a short topic that we will consider later on. Minimum glazing considering aesthetic, thermal, energy efficiency, acoustic, lighting issues in parallel with security issues. Then building cladding spanning floor to floor rather than connecting columns. So this is an interesting, let me get a quick drawing here. So if you see here, if you're connecting columns, these are your two columns here in this case. So this becomes these are the two columns, and if you span them this way, this is, so building a cladding spanning floor to floor rather than connecting to columns avoids major structural damage. This is just in how you design. For example, if you can have a continuous that connects into the beam itself, right? This way you're avoiding a blowout into, because it's hard to connect into a column, but into a beam and a slab, you're able to connect it better. So that way you're avoiding a blowout into the room itself behind it. So that is one thing to keep in mind. Then easily accessible cladding connections for replacement after the event. And again, the recesses that we talked about, one other reason is, apart from your vortex flow inside the recess, it's also to conceal, because that's a place where explosive devices can be concealed. Do you have any questions again so far? please do ask. It helps me also because I'm not speaking so much, right? So continuing further, features that facilitate again protection, avoid deep window sills and surface which can augment blast loading effects. Again, keep the windows in line with the structure, with the walls itself, and especially if the windows come out rather than come in, it also is a helpful feature. There are catch, you can have catch curtains in the back, but then those are additional things that you really need to do unless you don't need to do unless it is actually required. It's a very critical location. We go till what time? 12:15, right? No. 11. Oh, 11, no? So I better hurry up. We'll take as it goes. There's a lot more to go in the first one. But then avoid window openings. I talked about this. If required, have openings that outward rather than inward openings. Then coming to the structural frame. So this is where we as structural engineers come in and we're most comfortable within our zone, so to speak. So from a structural frame perspective, the essential requirement is the structure be well tied so that its overall inertia is used. What does it mean? In seismic, you go low mass, right? Low weight. Why do we lower the weight? Because you're going to reduce. What's that? Any other reason? Why do you want to reduce weight in a seismic environment? The building weight is lowered, right? Yeah? Inertial forces, right? So what is inertial forces? Mass times acceleration. So less mass, less inertial force. But in this case, what do you want? More inertia. So in blast, this is just the opposite. You want more inertia. So low weight, I should say lesser inertial forces. Now you see the interesting phenomenon here. You can't keep increasing your mass. You can build a fortress. And actually that Pentagon, the aircraft that came into it sort of blew into the Pentagon, there's a lot of lessons that were learned. And some of them was, of course, it had so many redundancies. So in terms of progressive collapse, there were so many lessons that were learned. Inertia also was fairly high, but that was also again because mass is high. But in a building, you still want to make it as efficient as possible, right? Now think of a building. Building is made of beams, columns, walls, slabs, right? If you design each one of them independently, when you do a structural analysis, what are you considering? Just beams, columns. So that forms your inertial component, right? Now if you start designing in a way, thinking differently, that I will take my wall into the stiffness considerations. For example, have you all jumped in a, what's that, bungee? Not bungee, what is that? Trampoline, right? Trampoline is very soft, right? Very not stiff at all. But once you jump, what happens? It becomes extremely stiff, right? So what are you doing? Because the trampoline is tied to all the sides. So stiffness, same thing. If you are tying your slab, you change the details of your slab to tie the slab to the beams and the columns very well. Now what are you increasing? You're not increasing mass. Ideally, more mass, more inertia. Now you're making the building act as one unit, right? Failure, you're not designing for, you do ultimately design for beams and columns as elements, but then in the analysis part of it, due to blast loading, you take the whole inertia, you're able to take the whole inertia of the building. So that's the goal. How do you increase the overall, this is overall building inertia. This is, let's say, to include beams, columns, walls, and slabs. So these are the primary, especially slabs. Then requires tensile capacity and ductility in design of elements and connections. Again, that tensile capacity comes in because you're now using the same trampoline effect, right? So you're now wanting to build in that tension that comes in the connections out there. Then reinforced concrete and steel framed buildings are ideally suited, but clearly that's not always the choice. Economics will dictate masonry, especially where we are. Wood is a primary choice. Then another thing that we consider, and we'll look into the progressive collapse, that's one topic, have multiple load paths. So let me go back a little bit. I want to spend just a minute on ductility. What is ductility? Can anybody define ductility? Deflect more without loss of load, right? That is the second part. Is a lot of structures deflect a lot, but without the loss of load is very important, right? So for example, I can take, let's say, a structure P versus, and you just take a simple beam and you're applying load P and it's going to deflect delta. So now in one case, P versus delta is going to go something like this, and then it fails. And in the other case, P versus delta is same deflection in both cases, right? Which one is more ductile? This is. Quite often, at least in my experience, I've seen people think ductile is a lot of deflection, forgetting about the second aspect of it. So keep that in mind. This is large deflections without or with minimal loss in peak load capacity. And it takes a lot of detailing, primarily detailing. This is not necessarily a strength criteria because you know the structures can achieve strength. Quite often it comes either your moment connections are detailed to this effect. Quite a few structures that are designed for blast are derived from principles of seismic detailing. So you start somewhere. So a lot of research has been done. For those of you who are not familiar with it, AISC, have you heard of AISC? It's the American Institute of Steel Construction. So this is www.aisc.org. So just like you have IS 800, AISC is the document, is the one they do what is known as ANSI 360. That's the steel design code. So they have put out a whole set of seismic manual. It's code, so it's not exactly a code. So they have a lot of seismic detailing requirements. You can purchase a whole book from that. So many of those principles. So ductility is ensured by proper detailing, and again you can say borrow principles of detailing from seismic design. And there is a variety design guides for detailing moment connections, especially in steel. There's a whole big book on that. You can always look into those resources. Then the other thing, we talked about multiple paths, load paths. So let me briefly talk about it. So for example, you have a building here this way. So quite often you design for loads coming down the column this way. So the loads are coming up and down the column in this manner. But when you design for multiple load paths, you also perhaps have to design this building for something like this. So now you have another pathway for the same load to come down. So this is pathway 1 and this is path 2. And you see now that will require additional design work, but at the same time it does add to certain costs. So there is all these things that need to be considered. Multiple load paths especially in design is very important. And you can't predict everything. So there are certain best that's why we are engineers, right? The word engineer, what does it mean? When you are engineering a building, you are all 15 of us or 20 of us can design it in different ways. But the building will behave the way you have designed it, right? Each solution is the right answer because the building load path is going to be the way you have designed it. If you don't want the load to go through a certain beam, you can design it that way. Make the beam less stiff, it will go. It's a very interesting, first time this was my very first building I designed, and I was M.Tech, I finished and I got this project to design a multi-story building, and we had a corridor and my boss wanted the corridor to be spanned by a beam, a continuous beam going all the way from, and then I saw the corridor is only about 1.5 meters or 5 feet wide, and the rooms are about 30 feet long, right? And then this particular beam was analysis wise, it was attracting so much moment. And I said, there's no way I'm going to design this for that moment. Why was it having so much moment? That beam that was spanning let's say you have a frame like this, right? It's a very simple concept. So now you're designing this particular beam. Why was this beam attracting so much moment? What is the stiffness of the beam? EI by, what is L? This is very small, right? So now this is 30 feet and this is 5 feet. So when it is that much stiffer, what is it going to do? Attract 6 times the moment. So these things you don't learn in a classroom, right? You go there and then you say, I can't design. Then what do? You separate the two buildings, make it a simply supported beam. So that way where the beam is. So these are some things to keep in mind as you practice. When you do even multiple load paths, you could run into issues like this. And then how to avoid it, what are other design aspects that you must consider. That's where engineers wise, we are really given very few opportunities to be creative. Architects are the creative ones. They've taken 95% of the creativity in a building. We bring in the creativities in this manner, right? Other simple things are consider at least a 3-bay wide frame building, avoiding cantilevered upward floors. We have talked about this. Floor slabs, we've also talked about this, tied into structural frame and designed to withstand load reversal. Right? Most of the times we are designing for loads gravity loads, but then explosions can be other way around too. So you'll have to reinforce in a different manner, particularly if and the way we consider slabs to be part of the inertia is the diaphragm action. So taking as part of the load resisting system itself, and this is very critical, the next one. Avoid brittle shear failure modes. Brittle shear failure modes, these are catastrophic. So detailing for shear and increasing shear capacities such that your goal in these cases are flexural capacities should govern. And primarily this is because these are more ductile behavior. Shear is a brittle behavior. Have internal structure core areas large enough to contain occupants unconnected to external street facing core areas such as lift wells. So you can evacuate, and so in this case the load from an explosive is not transferred to that particular structure, right? If you have an internal core which is, so you might have an outside core, for example. So this is your building, and then you could have, so this is part of the building, all of this, and then if you have a completely separated internal core, so you're going to be now recommending 2 walls or something like that to prevent, so that people are, it's hard to predict anyway, but there are, if that's an option, you could look into that. Then we talked of internal design. If you remember, these are the different things we looked at. Have diverse escape routes, well separated and evacuating in different directions. So again, these are, as engineers, we don't get exposed to blast design. Imagine architects. They are not going to be exposed to this at all. People are bridge architects. Bridges have architects working because it's still, you can make money and make a living out of it. But you're not going to make a living out of as an architect doing just blast designs. So often becomes an engineer's role to educate the architects. Critical facilities we talked about should be well internal defended parts and very robust internal partitions. These are all basically containment strategies. So what are some of the important documents? And again, I go with what is available and you should be able to download. And we'll look at several of these over this course. So the one is, when we talk of UFC, this is the United Facilities Criteria, UFCs. Now, I think as of October, some things, the way they are, the repositories are changing. Before they used to be, I think this website may not exist. I just checked. I think when we were designing the course, when I last taught the course, it was still there. But this is, I taught this in summer. I teach this course every summer, a course similar to this. WBDG is the whole building design guide. But now I think that goes under NBIS, and so the repositories may look different. But it will lead you to where you need to go. They haven't quite updated because the work started in October, I believe. So this is, DoD is the minimum anti-terrorism standards for building UFC 4-110. And there are other releases as well. Then the UFC, the one document we will be using quite extensively is 3-340-02. You read papers in this area, a lot of them will refer to 3-340-02. That is the structures to resist the effects of accidental explosions. This was based originally what is known as the TM5-1300, and the navies, they have their own, the air force, they have armies, navies and air force, they have all documents. All this have been combined into one in the 340-02. And then this is another part of this course again. This is 4-023 this is 03 is the year. This is design of buildings to resist progressive collapse. And then I've got a couple of documents. We'll go over this a little bit today. 22 is the latest version of it. ASCE standard. Although this is, now this committee, like ASCE is American Society of Civil Engineers. So Committee 7 works with load standards on loads. Committee 59 is on blast protection of buildings. They have updated, it doesn't get updated every 6 years as the others do, but this has got updated 11 years later. And then this is the committee for which I'm the chair. We worked quite hard to update this document. So hopefully this should be called 24 or 25. We worked through all the, there's a lot of process involved. It takes a couple of years. I started the process to update it in 2022. And 2024, I finished my term. It's continuing with the next chair, but it's still not completely voted in. So these things take 2 or 3 years. So, but this document you can purchase. This is not a free download. Both of them are not free, but the first 3 are publicly available.